Imagine waking up one day and being told that you live inside a giant hole in the universe. Not a black hole that would tear you apart, but a vast region where there is simply less stuff than average. Fewer galaxies, less matter, more emptiness. At first it sounds like a piece of poetic exaggeration, something a science communicator might say for dramatic effect. Yet this is a serious proposal from working cosmologists studying our cosmic neighbourhood. If it is true, it quietly touches almost everything we think we know about the universe. Stay with me, and if you enjoy journeys like this, tap like and subscribe so we can keep exploring together. On human scales, emptiness is rare. You're surrounded by walls, air, people, cities, and a planet under your feet. Our senses are tuned for crowded rooms and busy streets, not the scale where galaxies drift like dust. When you look up on a dark night, the sky itself feels full. Thousands of stars press against your eyes, and the glowing smear of the Milky Way stretches overhead like a river of light. It does not feel like we live in an empty place. It feels almost too crowded to breathe. Now stretch your imagination outward. Zoom away from Earth, past the other planets, past the outer edges of the solar system, until the sun itself shrinks to a pale speck. Keep going until entire constellations collapse into single points. At this scale, galaxies become the basic units of reality. They arrange themselves into a cosmic web, a vast pattern of filaments and walls, with huge dark regions in between. Those darker regions are not mistakes in the picture. They are cosmic voids, places where the density of matter is well below the cosmic average, where there are simply fewer galaxies than the universe would have if it were perfectly smooth. A void is not truly empty. There are still galaxies scattered through it, still dark matter threading space, still gas drifting in extremely thin streams. Compared to the rich clusters and bright filaments nearby, though, a void is a kind of cosmic countryside. Cities are rare, towns are small, and there are long stretches of quiet in between. When cosmologists talk about a void, they are talking about a region where the average density of matter dips below what you would expect if you smeared all the contents of the universe into an even fog. These regions are hundreds of millions of light years across. They are not little gaps, they are entire environments. Our story is about one such environment that seems to include us. Observations of galaxies around the Milky Way suggest that our local region is underdense out to very large distances. It is called the KBC Void, named after Keenan, Barger and Cowie, 3 astronomers who helped draw attention to it. The claim is not that we are sitting at the exact centre of a perfect bubble. It is that over a huge volume of space around us, the number of galaxies and the total amount of matter appear to be lower than the global cosmic average. The Milky Way is not alone, but it may be living in a somewhat quieter part of town. At first you might shrug and say that of course the universe has busier and quieter patches. Perhaps we just happen to live in one of the quieter ones. Yet this simple observation carries a much sharper edge. Modern cosmology rests on a guiding idea called the cosmological principle. It says that on large enough scales the universe should look roughly the same from any galaxy. No special vantage points, no privileged neighbourhoods. Our location is supposed to be typical, not remarkable. A void the size and depth of the KBC structure pushes hard on that comforting idea. It invites an uncomfortable question. Are we really in a typical place? Or have we been quietly assuming that our hometown is average when it might not be? This is not just about abstract fairness. Where we live in the cosmic web might change the numbers we measure when we look outward. If you're inside a large underdense region, gravity has a little less matter to work with, so it slows expansion less strongly than it would in a denser patch. From inside that bubble, the universe can look like it is expanding slightly faster than it truly is on average. That matters because one of the most important numbers in cosmology is the Hubble constant, the present-day rate of expansion of the universe. Different methods of measuring that number disagreed sharply in recent years, a puzzle known as the Hubble tension. Living inside a void is one of the most intriguing ways to tilt the odds in favour of a higher local value. So now the stakes are clear. The question is not only whether we live in a giant underdense region, it is whether that fact, if confirmed, is big enough to disturb our most precise cosmic measurements. Does the KBC void really exist as advertised? Is it as large, as deep and as clean as initial studies suggest? Could it be a statistical fluke that just happens to place us in a rare kind of neighbourhood? Or does it hint that our basic assumptions about uniformity on large scales need rethinking? Each of those possibilities leads to a very different story about what kind of universe we inhabit. In the rest of this journey, we will slow down and walk through that story carefully. We will learn what cosmic voids are and how they grow out of small ripples in the early universe. We will see how astronomers build three-dimensional maps of galaxies from a single planet, and how they first noticed that our own region seemed oddly underpopulated. Then we will follow the thread that ties this quiet neighborhood to the loud argument over the expansion rate of the universe. Along the way, we will meet simulations, philosophical worries about being special, and the strange comfort of knowing that even empty space can be full of meaning. For now, hold on to one simple idea. You may live inside a cosmic hole, but that hole might be one of the most interesting places a curious mind could hope to be. To understand why our neighborhood might be empty, we need to understand why the universe has any empty places at all. At first glance, this is backwards. The natural state of space should be nothing, and matter should be the rare visitor. Yet when you look at the night sky, it is the opposite. Stars are everywhere. Galaxies fill the darkness. The real puzzle is not why there are voids. It is why there are filaments, clusters, and glowing islands of light in the first place, and why they line up in such a complicated pattern. The story begins in the early universe, long before there were stars, planets, or galaxies. In that era, the cosmos was a hot, nearly uniform sea of particles and radiation. The key word here is nearly. It was not perfectly smooth. There were tiny ripples in density, places that were slightly more crowded or slightly more sparse than their surroundings. The differences were ridiculously small. Imagine taking the entire universe and changing the density in one region by about 1 part in 100,000. That is the level of unevenness we're talking about. Those ripples are frozen in the oldest light we can see, the glow of the cosmic microwave background. This is the cooled remnant of the early fireball, a kind of baby picture of the universe taken when it was only a few 100,000 years old. When we map it carefully, we see patches that are a little warmer and a little cooler. Warmer regions correspond to slightly underdense spots. Cooler regions mark slightly overdense ones. The temperature differences are small, but they tell us exactly where gravity had a head start. Now add time and let gravity do what gravity does. In slightly overdense regions, there is a bit more mass. That extra mass gives gravity a tiny edge, which pulls in more material from nearby. As matter flows in, the region becomes even denser, which strengthens its pull. Over billions of years, those small advantages grow into the massive clusters and bright filaments of galaxies we see today. These are the cosmic downtowns, the places where the universe builds cities of stars. In slightly underdense regions, the opposite happens. There is a bit less mass for gravity to work with. Matter tends to flow out of these regions toward their denser neighbours. The underdense patches become more and more depleted. They puff up as the universe expands and their boundaries are stretched by surrounding structures. Over time, they sharpen into the great cavities of the cosmic web, where initial overdensities become walls and filaments, initial underdensities mature into voids. It helps to picture a loaf of rising bread filled with raisins. The dough stands in for space itself. The raisins are galaxies. As the dough expands, every raisin moves away from every other. Now imagine that some regions of the dough begin denser than others. In the denser regions, raisins are closer, and gravity tugs them together into clumps. In less dense regions, raisins drift away more easily, and the spaces between them grow faster. After enough time, you get a structure that is not uniform at all. There are swollen gaps and dense clusters. The universe has followed a similar recipe, though with dark matter and physics instead of flour and yeast. Dark matter is an invisible form of matter that does not emit light, but does feel and produce gravity. It dominates the mass budget of the universe. In the early cosmos, dark matter formed the skeleton of structure. Its distribution set the pattern of future galaxies. Where dark matter was a little denser, it collapsed into halos that later lit up with stars and gas. Where it was a little sparser, it expanded and drained away. Voids today are not just empty of galaxies. They are underdense in dark matter as well. They are literally regions where the main ingredient of structure is missing. Because the universe is expanding, all distances grow over time. However, the rate at which distances grow can differ slightly between regions that are more or less dense than average. In overdense regions, gravity partially resists expansion. In underdense regions, there is less gravitational pull trying to hold things together, so expansion wins more easily. Over billions of years, voids not only become emptier, they also effectively expand a bit faster than the universe as a whole. They are like balloons inside a larger balloon, inflating more quickly than their surroundings. From simulations of structure formation, cosmologists have learned that voids are not rare accidents. They are a natural and expected feature of a universe that starts with small density fluctuations and evolves under gravity in an expanding background. The cosmic web is the end result of this long, slow dance. Galaxies outline the denser parts. Voids fill the spaces in between. A typical void in these simulations can be tens of millions of light-years across, sometimes even hundreds of millions. They are stitched together, cluster against cluster, like the gaps in a three-dimensional honeycomb. However, there is an important subtlety. Not all voids are created equal. Some are small, shallow depressions, barely underdense compared to their surroundings. Others are deep and expansive, stretching across a significant fraction of the cosmic map. The statistics of these voids carry information about the underlying cosmological model. If you change the amount of dark matter, or the properties of dark energy, or the spectrum of the initial fluctuations, you change how many voids you get of each size and depth. Measuring voids is another way of testing whether our model of the universe is correct. In a universe dominated by dark matter and dark energy, with gravity described by general relativity and initial fluctuations set by early cosmic processes, there is a prediction for how extreme a void can reasonably be. You can simulate many universes, draw random observers, and ask what kind of void each one is likely to see around them. Most will live in fairly ordinary neighborhoods. A small fraction will live closer to a big underdensity. An even smaller fraction will find themselves inside a giant deep void that stretches for hundreds of millions of light-years. That tiny fraction is supposed to be very small. This is where our local situation becomes interesting. Voids the size of ordinary gaps in the cosmic web are no surprise. They are baked into the theory. But when we map the environment around the Milky Way and its neighbours, the underdensity that emerges appears to sit toward the upper end of what is expected. Not impossible on paper, but rare enough that it raises eyebrows. If simulations say that only a very small fraction of observers should find themselves in such a deep, extended void, then the fact that we might be among them demands attention. It could be a stroke of statistical luck. It could be a hint that our model needs adjusting. So the basic story is simple, even if the details are fierce. Start with a nearly smooth universe, sprinkle it with tiny fluctuations, and let gravity and expansion run for billions of years. Overdensities grow into clusters and filaments. Underdensities deepen into voids. A rich cosmic web appears with structure on many scales. That web is not decoration. It shapes the motions of galaxies, the path of light, and the measurements of cosmic expansion that we make from our quiet little planet. In the next part, we will see how, from this single speck of rock, astronomers learned to map that web and discovered the suspicion that our own thread runs through an unusually large patch of almost nothing. From the surface of Earth, the universe looks flat. The stars appear painted on a dark dome and the Milky Way is just a band of light. Your eyes have almost no sense of depth at these scales. A bright star might be close or incredibly far away. A faint smudge might be a nearby cloud or a distant galaxy. To turn that flat picture into a three-dimensional map, astronomers had to learn how to measure distance and motion, using nothing more than the light that arrives at our telescopes. The first key idea is that light can act as a speedometer. When a galaxy moves away from us, the light we receive from it is stretched toward longer, redder wavelengths. This effect is called redshift. The faster the galaxy recedes, the larger its redshift number becomes. In the early 20th century, astronomers measured redshifts for nearby galaxies and compared them to independent distance estimates. They found a striking trend. More distant galaxies tended to be moving away faster. That relationship became known as the Hubble-Lemaitre law. In simple terms, double the distance and you roughly double the recession speed. However, velocity alone does not give distance. To build a map, you need at least one reliable way to say how far away a given galaxy is. That is where distance indicators come in. Some stars behave like natural beacons. Cepheid variable stars pulse with periods that are tightly linked to their true brightness. Measure how bright a Cepheid appears from Earth, Compare it to the brightness it ought to have, and you can infer how far away it is. Certain kinds of stellar explosions called Type 1, a supernovae, also reach nearly the same peak brightness each time. They can light up galaxies so distant that individual stars are otherwise invisible. Together, these and other methods form what astronomers call a distance ladder, a chain of overlapping techniques that climb from nearby stars to remote galaxies. Once you have both a redshift and a distance for many galaxies, you can begin to place them in three-dimensional space. Each galaxy gets a position on the sky and a distance estimate along the line of sight. Early surveys did this for a few hundred objects. Later ones, like the Sloan Digital Sky Survey and its companions, did it for hundreds of thousands and then millions. When you plot those points, something remarkable appears. The distribution of galaxies is not random. It forms strands, sheets, and clusters with huge dark gaps in between. You can slice through this map and see the cosmic web etched in data, like a spider web drawn in points of light. These maps are not perfect. They carry the fingerprints of both cosmic expansion and local gravitational motions. On large scales, galaxies ride the general expansion of the universe, moving away in a smooth pattern. On smaller scales, gravity from nearby structures tugs them around, adding peculiar velocities on top of the overall flow. A galaxy falling toward a cluster may move slightly faster or slower than the pure expansion would predict. In redshift space, this can stretch or squash structures along our line of sight. Clusters can look elongated. Dense regions can seem compressed. To recover the true layout of matter, cosmologists must disentangle global expansion from these local wiggles. Doing that requires both physics and statistics. You start with a model of the universe that says how structures grow and how galaxies should move in response to gravity. You simulate that universe, measure how peculiar motions distort your map, and then design corrections that can be applied to real data. You also smooth over small-scale noise by averaging galaxy properties in larger volumes like pixels in 3 dimensions. The result is a reconstruction of the density field, an estimate of where the universe is richer in matter and where it is poorer. When you color-code that map, clusters glow warm and bright while voids sink into cold blues and blacks. Of course, there are complications baked in from the beginning. Our view of the sky is partly blocked by the plane of the Milky Way, where dust and stars obscure background galaxies. Surveys have limited sensitivity, so they miss faint galaxies beyond a certain distance. The farther out you look, the more your catalogue is dominated by the brightest galaxies, which can bias counts. Astronomers work hard to correct for these selection effects, modelling what they expect to see if the universe were perfectly uniform, and then comparing it to the actual counts. Every step adds uncertainty, but also adds power. With each new generation of surveys, the cosmic web image sharpens. For our story, one particular kind of measurement is crucial. Instead of just looking at patterns on the sky, you can count how many galaxies you see within spherical shells at different distances and compare those counts to what you expect from a globally averaged universe. Imagine drawing a series of expanding bubbles around the Milky Way and asking how much total light or mass is contained in each shell. If the universe is homogeneous on large scales and our position is reasonably typical, then beyond some distance the average density in those shells should settle toward a constant value. Local bumps and dips should wash out. When teams performed this exercise for our cosmic neighbourhood, they found something odd. Within a few 100 million light-years, the density of galaxies and their total luminosity appeared lower than the value inferred from much larger scales. As they pushed the radius of their shells outward, the density slowly climbed, approaching the expected average only at distances of several 100 million to perhaps 1 billion light-years. That pattern is exactly what you would expect if we lived inside a large underdense region that gradually transitions to normal density beyond its edges. It was not a single missing cluster or a random patch of bad data. It looked like a genuine feature of our environment. This is how, from a single rocky planet orbiting an ordinary star, we learned to see the cosmos in 3 dimensions and began to suspect that our home lies inside a vast hollow of the cosmic web. Every dot on those plots is a real galaxy, with its own stars and planets. But when you stand back and look at the pattern, you see something bigger. You see the skeleton of the universe and the strange cavity that appears to surround us. In the next part, we will focus on the astronomers who first traced that cavity in detail and gave it a name, and we will ask just how certain we can be that the KBC Void is real. The idea that we live inside a giant underdense region did not appear in a single dramatic moment. It crept in through the slow, patient work of people counting galaxies. In some ways, this is the most humble part of the story. No new fundamental force, no exotic particle, just astronomers asking a simple question. How much light is there around us compared to the rest of the universe? That question, pursued carefully enough, turned into a challenge to one of cosmology's quiet assumptions. One of the most important early pushes came from a team led by Keenan, Barger and Cowie. They set out to measure the total amount of starlight in different shells around us, using galaxy surveys that reach far beyond the local group. Instead of focusing on individual galaxies, they looked at luminosity density. How much light do you get per unit volume of space, averaged over many galaxies at a given distance? The idea was straightforward. If the universe is homogeneous on large scales and our position is not unusual, then beyond some radius, the luminosity density should settle down to the same value you see in very distant surveys. To make that comparison fair, they used wavelengths of light that track the total mass in stars rather than short-term bursts of star formation. In practice, that meant focusing on near-infrared bands where old stars glow steadily and dust has less power to hide them. They combined data from different surveys that sample the sky out to a range of distances, stitching them into a single profile of light around our position. Imagine drawing a series of concentric shells around the Milky Way and asking how brightly each shell shines. That profile, once corrected for selection effects and survey limits, becomes a fingerprint of the matter distribution. What they found was unsettling. In the inner shells, out to a few 100 million light-years, the luminosity density was significantly lower than the value inferred from surveys that probe out to much larger distances. As they pushed the radius outward, the density gently climbed, approaching the global average only beyond several 100 million to perhaps close to 1 billion light-years. The inner region looked like a bowl that had been scooped out. Fewer galaxies, less starlight, less matter. It was not a tiny dip. It was a broad, coherent underdensity that seemed to enclose our whole neighbourhood. You might worry that this could be a trick of incomplete data. Perhaps the surveys used in the inner region were missing faint galaxies. Perhaps the bright galaxies used as tracers were distributed in an unusual way. The team knew this and spent a great deal of effort checking for such pitfalls. They compared different catalogues. They tested how robust their results were to changes in selection cuts and corrections. The underdensity remained. Not perfectly sharp, not perfectly spherical, but persistent enough that it demanded a name. They began to speak of a local void, a KBC scale underdensity surrounding us. Other groups approached the problem from different angles and landed on broadly similar hints. Some counted galaxies directly, rather than focusing on luminosity. Others studied peculiar velocities, the motions of galaxies relative to the smooth expansion field, to infer the underlying density in our region of space. If you live inside an underdense bubble, galaxies tend to flow outward from it toward denser structures at its edges. Those flows leave signatures in velocity maps. While the details varied from study to study, the general picture kept returning. Our cosmic neighbourhood did not seem as richly populated as one might expect from global averages. None of these measurements is clean. Each involves messy steps, correcting for the fact that the Milky Way hides part of the sky, accounting for the limits of different telescopes, harmonizing catalogues that were designed with different goals in mind. When you build a result by balancing many small corrections, there is always the risk that a hidden bias sneaks through. The scientists involved were keenly aware of this. Much of the technical debate over the KBC Void has focused on exactly these issues. Are we seeing a real feature, or a subtle shadow cast by our own methods? Yet even when you take those worries seriously, the basic fact remains hard to escape. When you compare our local counts of galaxies and starlight to what the standard cosmological model suggests should be typical on scales of a few 100 million light-years, we fall low. Not catastrophically low, but low enough that it matters. The simplest way to summarize this is to say that we appear to live in a region with a significantly reduced matter density compared to the cosmic mean, a region that extends over hundreds of millions of light-years before blending back into the average universe. One crucial question is how deep and how large this underdensity really is. The deeper and larger it is, the more it can influence our measurements of cosmic expansion. If the KBC Void is only a shallow depression, then it is just another feature of the web. Interesting, but not world-changing. If it is deep and nearly spherical on very large scales, then it has the power to bias local measurements of the Hubble constant and other parameters. Different studies have produced slightly different estimates for its depth and radius, but many fall into the provocative range where the void is neither trivial nor impossible. Another question is where exactly we sit inside this structure. Cosmologists sometimes model the void as roughly spherical and place us near its center for simplicity, but real space is messier. The underdensity may be lopsided or connected to other structures. We may be off-center, closer to one wall of the surrounding web. These details matter for precise calculations of how much the void can distort our view of cosmic expansion, but they do not change the broad picture. We seem to live in a region that is noticeably less crowded than the average universe predicted by our best models. By the time the term KBC Void had entered the conversation, the idea had slipped from speculation into a live hypothesis. Not everyone agreed on its exact properties. Some argued that the underdensity was overinterpreted, that newer and deeper surveys would smooth it out. Others pointed out that even if the void were real, it might not be extreme enough to fully explain the Hubble tension. But almost no one dismissed the basic observation as pure imagination. The data had spoken clearly enough to demand attention, so from the careful counting of galaxies and the quiet glow of starlight, a remarkable possibility emerged. Our Milky Way and its neighbours might be floating in the middle of a vast, relatively empty basin of the cosmic web. That basin now has a name and a personality in the story of modern cosmology. In the next part, we will ask how unusual such a structure really is in the universe we think we understand. We will look to simulations and statistics to decide whether the KBC Void is a rare but acceptable fluctuation, or a sign that something deeper in our model needs to be revised. When you first hear that we might live in a giant cosmic void, it feels strange but not impossible. The universe is big. Weird things happen. Somewhere out there, someone has to win the lottery. The real question is how often that kind of lottery win is supposed to happen in our best model of the universe. Are we talking about a rare neighbour that shows up every now and then, or something so extreme that its existence hints that our picture of reality is missing a piece? To answer that, cosmologists turn to their most powerful laboratory, the simulated universe inside a computer. In these simulations, you start with a box of virtual space filled with dark matter and ordinary matter, expanding the way the real universe does. The initial conditions are tuned to match what we see in the cosmic microwave background, those tiny ripples of slightly higher and slightly lower density. Then you let gravity and expansion run forward for billions of years. What emerges is a cosmic web of filaments and voids, clusters and superclusters, not drawn by hand but grown by physics. In each of these simulated universes, you can sprinkle imaginary observers on random galaxies and ask what their surroundings look like. For each observer, you can measure the density of matter around them in a series of spheres of different radii, just as the KBC team did with real data. Most observers live in environments that are close to the cosmic average once you look on large enough scales. A few find themselves near clusters or superclusters. A smaller set lives inside noticeable underdensities. The distribution of these environments is what really matters. It tells you how often a KBC-sized void should appear in a universe governed by our standard cosmology. Now, imagine ranking voids by how extreme they are. Some are mild dips, only a bit less dense than average. Some are deep hollows that stand out clearly in the density field. In statistics, you might describe these extremes in terms of standard deviations, a measure of how far from the mean a given fluctuation lies. In a simple random field, a 3 sigma event is unusual but not shocking. A 4 or 5 sigma event would be vanishingly rare. The details are more subtle in full cosmological simulations, but the spirit is the same. You ask how often you should see voids of a given depth and size. When researchers carry out this exercise, they find that large voids are allowed but become rapidly less common as you push to bigger radii and deeper dips. A void that is modest in size and underdensity can be found almost everywhere. A void that spans hundreds of millions of light years and is significantly below the cosmic mean is more unusual. The KBC Void, as currently inferred, appears to land in a regime that is not impossible, but also not comfortably ordinary. Some analyses suggest that having such a large underdensity centered near our position would be a once in many hundreds or thousands kind of event. Others, using different assumptions, find slightly less dramatic odds. Here is where interpretation becomes tricky. A rare event is not the same as an impossible event. If you roll a fair die enough times, you will eventually get 6 sixes in a row, even though that outcome is unlikely on any single attempt. If the universe is large enough and filled with enough galaxies, you expect some observers to live in environments that are statistically weird. The fact that we might be among them is not by itself a proof that the model is wrong. It does, however, force a kind of existential shrug. How comfortable are we with the idea that our cosmic address is drawn from the thin tail of the distribution? There is another layer of complication. The KBC Void is not just any rare structure. It sits in a very particular place. It surrounds us. That fact makes people nervous in a way that an equally rare void far away does not. Cosmology has been built on the idea that we are not in a privileged spot. The cosmological principle says that, on large scales, the universe should look statistically similar from any galaxy. This does not forbid local structure. It does not say we cannot live near a cluster or near a void. It simply assumes that such features average out when you look on scales big enough. A structure that appears to stretch across a significant fraction of a billion light-years pokes at that assumption. Simulations can also be used to ask a more pointed question. If you select observers who live in voids as deep and extended as the KBC structure, what else do they tend to measure? Do they infer a higher Hubble constant than observers elsewhere? Do they see different flows of galaxies on large scales? In many models, the answer is yes. Observers inside large underdensities measure slightly faster local expansion rates than the global average, exactly because there is less matter to slow expansion. The shift is usually on the order of a few to perhaps 10%, depending on the details of the void. That sounds small, but it is exactly the range that matters in the current Hubble tension. The challenge is that, when you combine all these lines of evidence, you end up in an awkward middle ground. On the one hand, a KBC-like void is not so extreme that it flatly contradicts standard cosmology. You can find similar structures in some simulated universes, though not frequently. On the other hand, it is extreme enough that many cosmologists hesitate to accept it as just a random quirk, without looking very hard for alternative explanations. That hesitation is amplified by the coincidence that the existence of such a void would conveniently push local measurements of the Hubble constant in the direction we actually observe. This is where the idea of fine-tuning creeps in. If the only way to reconcile a large underdensity with our models is to say that we got a very rare draw from the cosmic lottery, and that this rare draw just happens to help explain another puzzling measurement, then you're tempted to suspect that your model or your interpretation might be incomplete. Maybe the void is not as deep as early studies suggest. Maybe systematics in the surveys mimic an underdensity. Maybe the underlying cosmological model needs adjustment in the amount of dark matter or the behavior of dark energy, which would change the expected statistics of voids. There is also the possibility that our intuition about what counts as too rare is not very reliable in a universe this large. We have exactly one observable cosmos to study. We cannot see beyond our horizon. We cannot rewind and rerun the initial conditions. Simulations help, but they are built on the same assumptions we're trying to test. When those simulations say that a given void configuration is allowed but unlikely, we're still left to decide what to do with that judgment. Do we treat the KBC void as a valuable anomaly, a clue that maybe something deeper is going on? Or do we treat it as a curiosity that stretches our patience but not yet the model itself? For now, the honest answer is that we do not yet know how big is too big. The KBC void lives in a parameter space that is still being mapped. As more detailed surveys arrive and as simulations grow in resolution and volume, the error bars on its properties and its expected frequency will shrink. The universe will either gently nudge the void back into the safe zone of rare but ordinary fluctuations, or push it further out into the realm where explanations like random chance start to feel hollow. In the next part, we will return to the cosmological principle and ask how much strain a structure like this really puts on the idea that our place in the universe is not special. When cosmologists say that the universe is simple, they do not mean it looks simple. The sky is a chaos of structures. There are clusters, filaments, walls, and voids. Yet beneath that complexity is a very strong guiding hunch. On large enough scales, the universe should look statistically the same no matter where you stand or which direction you look. This idea is called the cosmological principle. It is the quiet assumption that lets us talk about a single cosmic expansion rate, a single average matter density, and a single history that applies to everyone. The principle has two parts. Homogeneity means that if you could blur your view over very large volumes, the universe would have the same average properties everywhere. Isotropy means that from any given place, the universe looks roughly the same in every direction. Together they say that we do not live in a privileged corner. Our galaxy is not at the centre of anything. We are just one more observer drifting in a universe that does not care where we are. This idea is not proven from first principles. It is a working hypothesis that has survived many tests. What worries people about the KBC Void is not simply that it exists, but that it seems large enough to bump against this principle. If we live inside a region that is hundreds of millions of light years across and substantially underdense, does that mean the universe has broken its promise to be ordinary on large scales? Is the cosmological principle just a convenient story we tell ourselves while ignoring the huge hollow under our feet? To answer that, we have to be careful about scales. The cosmological principle has never claimed that the universe is featureless. On small and medium scales, structure is expected and observed. Galaxies, clusters, filaments, and voids are all part of the deal. The principle only asserts that if you average over sufficiently large regions, these inhomogeneities fade into a smooth background. The tricky question becomes what counts as sufficiently large. If you need to average over distances larger than we can comfortably survey, the principle becomes harder to test and easier to take on faith. Observations provide some important anchors. The cosmic microwave background is astonishingly uniform. Temperature fluctuations on the sky are tiny and follow statistical patterns that match a nearly homogeneous, nearly isotropic universe on very large scales. Galaxy surveys that reach out billions of light years show that, when you average over big enough volumes, the number of galaxies per unit volume stabilizes. Fluctuations remain, but their relative size decreases as your sample volume grows. Both of these facts support the idea that the universe is in some sense smooth on the larger scales we can see. Living in a void does not automatically violate that story. If voids and clusters are sprinkled around in a way that still averages out on very large scales, then the cosmological principle can coexist with the idea that any given observer might live in a somewhat atypical patch. From this perspective, the KBC Void is just one piece of the cosmic web. It may be more dramatic than average, but as long as similar structures exist elsewhere and the global statistics remain unchanged, the principle can survive. The universe can still be homogeneous in the sense that its roughness is the same everywhere. Yet there is a different, more psychological way the principle gets tested. Even if big voids exist in many places, finding that we live in one of the largest and deepest examples feels suspicious. The principle is often taken to mean not only that the universe looks similar everywhere, but also that we ourselves are typical on large scales. That is sometimes called the Copernican spirit, the tendency to remove ourselves from any special pedestal. If only a very small fraction of observers should live in a KBC-type void, and we appear to be among them, then our sense of being typical takes a hit. Some researchers respond by weakening the philosophical load carried by the principle. They point out that homogeneity and isotropy are statements about the universe as a whole, not about our exact location. The principle says that it is possible to describe the universe in terms of a smooth background with small perturbations. It does not promise that no observer will ever find themselves in a weird spot. In this view, the KBC Void is a stress test, not a fatal blow. It forces us to check whether our models and surveys really support the assumption of large-scale uniformity, but it does not overthrow the entire framework on its own. Others take a more cautious stance. They worry that we may have been too quick to lean on the cosmological principle when building our models. By assuming homogeneity and isotropy, we simplify Einstein's equations for gravity into a neat, solvable form. That gives us a powerful model of cosmic expansion, dark matter and dark energy. But if the real universe has large-scale inhomogeneities that are more extreme than we thought, those simplifications might hide important effects. Living in a big void could subtly alter the way light travels to us. the way we infer distances, and the way we interpret redshifts. In that case, the principle would not just be an innocent assumption, it would be an approximation whose limits we may be crossing. There are also more radical proposals that try to turn the situation upside down. A few theorists have suggested that we might live in such a large and deep void that what we interpret as cosmic acceleration, usually attributed to dark energy, is really an illusion created by our lopsided environment. In these models, the universe as a whole might not be accelerating at all. Instead, observers in a central underdensity misread the pattern of redshifts and distances because they assume homogeneity where there is none. These models are highly constrained by data and have trouble matching all observations at once, but they show how deeply the cosmological principle is woven into our interpretation of the sky. For now, most cosmologists still treat the principle as a good approximation. The cosmic microwave background is too smooth. Large-scale surveys look too regular. Alternative models without large-scale homogeneity struggle to beat the standard picture. The KBC Void, if it is as large and deep as some analyses suggest, sits near the edge of what that picture can comfortably accommodate. It does not clearly break the principle, but it pushes against it, asking us to sharpen both our measurements and our language. Perhaps the most honest way to put it is this: the cosmological principle is not a law of nature handed down from above. It is a practical, elegant guess that has worked extremely well so far. The discovery of a giant local void does not demolish it, but it does remind us that our assumptions live on probation. They survive only as long as data continue to support them. In the next part, we will step away from philosophy and return to hard numbers, looking at how different methods measure the expansion rate of the universe and why the Hubble constant has become the central number in this entire debate. If you want to know whether the universe is behaving strangely in our neighbourhood, you first need a clear idea of how fast it is expanding overall. That sounds easy. Pick a number, call it the Hubble constant, and be done. In practice, this number has become one of the most contentious in modern science. Two powerful and carefully checked methods give answers that do not agree. The gap is not enormous, but it is persistent and precise, which makes it feel less like a simple mistake and more like a clue. Our possible home inside a void enters the story because it could bend this number in subtle ways. The Hubble constant tells you how fast distant galaxies recede on average as a function of their distance. If the value was 70, you would read that as 70 kilometers per second of recession speed for every megaparsec of distance, where a megaparsec is a little over 3 million light-years. Double the distance, double the typical recession speed. This is not because galaxies are flying through space like bullets. It is because space itself is stretching, carrying galaxies along with it. The Hubble constant is a single snapshot of that stretching rate today. The first way we measure it starts with nearby objects whose distances we can know with high confidence. This is the distance ladder. At the lowest rung are stars whose distances can be measured by parallax, a simple geometric effect. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant ones. Measure that shift and you can calculate their distance using high school trigonometry. Space telescopes have turned this old trick into a precision tool, pinning down distances to many nearby stars with exquisite accuracy. From those stars we climb to Cepheid variables. These are stars that brighten and dim in a predictable cycle. The longer the period of their pulse, the brighter they truly are. Once you know that relationship, you can use parallax-measured Cepheids to calibrate the rule that links period to brightness. Then, when you see a Cepheid in a more distant galaxy, you can infer how bright it must really be. Compare that to how bright it appears, and work out its distance. In this way, Cepheids become cosmic lighthouses that carry the parallax information outward into the universe. The next rung involves Type 1 a supernovae. These stellar explosions reach nearly the same peak luminosity each time, making them standard candles for even greater distances. You calibrate their true brightness, using the galaxies whose distances have already been fixed by Cepheids, then apply that calibration to supernovae in galaxies that lie much farther away. Combine those distances with their redshifts, and you draw a line of recession speed versus distance. The slope of that line is your local measurement of the Hubble constant. This late universe method relies on real explosions and real stars, all relatively nearby in cosmic terms. The second way to measure the expansion rate reaches back almost to the beginning of time. It uses the cosmic microwave background, that faint afterglow from when the universe was still a hot, dense plasma. Tiny fluctuations in the temperature and polarization of this background carry information about the contents of the universe and its geometry. When satellites map this glow across the whole sky and analyze its statistical patterns, they can infer parameters such as the density of dark matter, the density of ordinary matter, and the curvature of space. These parameters feed into a cosmological model that describes how the universe expands from its early hot state to the present. In this approach, you're not directly measuring the Hubble constant today. Instead, you're measuring the initial conditions and the rules of the game, then letting the equations evolve forward to see what expansion rate they predict now. It is like watching a slow-motion replay of the cosmos and checking what the clock reads in the current frame. This early universe method is powerful because it uses physics from a very different era and does not depend on the details of the local galaxy population. Here is the problem. The distance ladder method and the early universe method give values for the Hubble constant that differ by several units on the usual scale. The late universe measurements tend to favor a higher expansion rate. The cosmic microwave background-based model tends to favor a lower one. Both sides have shrunk their error bars over the years, checking for systematic mistakes, recalibrating instruments, revisiting assumptions. Instead of the two ranges creeping toward each other, they have remained stubbornly apart. The overlap has shrunk. The tension has grown. This mismatch is what people call the Hubble tension. It is not that the numbers are wildly incompatible. It is that the disagreement is now precise, stable, and difficult to blame on obvious errors. If only one method existed, we would simply quote a value and move on. Because two independent and sophisticated methods exist, they serve as cross-checks on one another. Each one insists that it is correct within its quoted uncertainties. Both have passed a long list of internal tests. That is what makes the tension feel like a real puzzle, rather than a bookkeeping issue. There are several possible ways out. One is that one or both methods still harbour hidden systematics, subtle biases that have not yet been fully understood. Perhaps distance indicators are more complicated than we think. Perhaps our model of dust, stellar populations, or supernova behaviour needs refinement. On the cosmic microwave background side, perhaps there are unrecognised degeneracies in the parameters or missing physics that slightly shifts the inferred expansion rate. Consider how many small corrections go into these analyses, and it is easy to imagine that one has been misjudged. Yet as teams keep checking, confidence in both methods has actually increased. Another possibility is that our standard cosmological model is incomplete. The model assumes a simple mixture of components: dark matter, ordinary matter, and dark energy behaving in specific ways. If any of those assumptions is wrong, the link between early universe measurements and the present expansion rate could be altered. People have explored ideas that add new relativistic particles, modify the properties of dark energy, or tweak gravity itself. Many of these proposals struggle to fit all existing data, but the fact that they are being seriously examined shows how important the Hubble constant has become as a window into possible new physics. This is where our suspected void steps in. If we live in a region that is less dense than average, then local measurements using Cepheids and supernovae might naturally produce a higher value for the Hubble constant than the true global average. There is simply less matter in our vicinity to slow the expansion, so the local stretching of space is slightly faster. The cosmic microwave background, by contrast, measures conditions on scales far larger than any one void, and so reflects something closer to the true cosmic mean. In this picture, the Hubble tension is partly an illusion created by our unusual location. How far this idea can go depends on the depth and size of the KBC void. A shallow underdensity would barely move the needle. A deep and extended one could shift the locally inferred expansion rate by several %, perhaps enough to ease the tension significantly, though likely not to erase it entirely. In the next part, we will follow this idea more closely. We will step inside a simulated universe, drop observers into voids like ours, and see what they would measure. That will tell us whether living in a giant underdense region can really account for the stubborn disagreement over how fast the universe is growing today. Now we can finally ask the question that has been hiding underneath our whole journey. If we truly live in a giant underdense region, can that fact alone explain why nearby galaxies seem to tell us that the universe is expanding faster than the early universe data suggests? Could the KBC Void be the missing ingredient that turns the Hubble tension from a crisis into a misunderstanding? To build intuition, picture two very different cosmic neighborhoods. In one, matter is crowded, galaxies are packed into clusters, filaments crisscross the sky, and dark matter halos overlap and tug on one another. Gravity in that region is strong on average, always trying to pull things back together, always fighting the expansion of space. In the other neighborhood, matter is sparse, galaxies are scattered, and the dark matter field is thin. Gravity has less to work with, so it slows expansion less effectively. As the universe grows, the dense region lags slightly behind the global expansion, and the empty region runs a little ahead. From inside the dense region, if you measure how fast nearby galaxies recede and turn that into a Hubble constant, you will infer a slightly lower expansion rate than the global average. From inside the underdense region, you will infer a slightly higher rate. Nothing magical is happening. You're simply reading the expansion of space as modified by the local distribution of matter. If you then compare your local measurement to a value inferred from the cosmic microwave background, which averages over huge volumes and mostly ignores any one void, the two numbers can differ in exactly the way we observe. This idea has been turned into more formal models. Cosmologists describe a universe that is almost homogeneous, but contains a spherically symmetric underdense region around us. They solve Einstein's equations for this lumpy geometry and compute how light travels from distant galaxies through the void and into our telescopes. From those light paths and redshifts, they can reconstruct what a local observer would infer about distances and expansion, and how those inferences differ from the true global values. The equations are complicated, but the result is simple. Living in a void tends to make the universe look like it is expanding faster than it really is. The key questions are how strong that effect is, and whether a void with properties similar to the KBC structure can produce a shift as large as the observed Hubble tension. If the void is shallow, meaning only slightly underdense, the change in the locally inferred Hubble constant is tiny. It might move the value by 1 or 2%, far too little to matter. If the void is deeper and stretches over several 100 million light years, the shift can grow to several percent. That begins to sound interesting, because the mismatch between the early and late universe measurements lives in roughly that range. Researchers have played a kind of numerical game with this. They dial the depth and size of the void up and down in their models and watch how the local Hubble value responds. For small radii, the effect is strong but highly local and tends to be washed out when you include more distant supernovae in your analysis. For larger radii, the effect becomes smoother and more coherent, so it influences a wider range of distance measurements. There is a sweet spot where the void is big enough and deep enough to raise the local Hubble constant by a noticeable amount without obviously contradicting other observations. The KBC Void, as inferred from galaxy counts, was suggested to sit close to that sweet spot. However, the universe rarely grants easy victories. When you fold in more detailed data, the story becomes more nuanced. Supernovae used in distance ladder measurements are not confined to our immediate region. Many live in galaxies whose light has travelled well beyond the suspected edge of the KBC Void. If the underdensity were the only reason for a high local Hubble constant, you might expect that including more distant supernovae would gradually pull the inferred value back toward the global mean. In practice, the tension remains stubborn even as the sample grows, which suggests that the void on its own cannot be the whole story. Simulations of structure formation add another layer. When cosmologists populate a simulated universe with galaxies and then choose observer positions inside large voids, they can directly compute what those observers would measure for the Hubble constant, using realistic survey strategies. The result is that living in a void can indeed bias the local expansion rate upward, but typically not enough to fully bridge the gap between the cosmic microwave background value and the distance ladder value. In many cases, the predicted shift is a fraction of the observed tension. It eases the disagreement but does not erase it. There is also the question of consistency with other measurements. A very deep and extended void would not only affect the Hubble constant, it would imprint itself on patterns of galaxy motions, on weak gravitational lensing of background galaxies, and on the detailed statistics of large-scale structure. Some of those signatures can be searched for in current data. So far, they lean against the idea of an extremely dramatic local underdensity, though they do not rule out a moderate one. That again points toward the same conclusion. The KBC Void, if real, is a piece of the puzzle rather than the entire solution. So can a giant void explain the Hubble tension? The most balanced answer is that it can plausibly account for some of it. Living in an underdense region naturally pushes our locally measured Hubble constant upward. The deeper and larger the void, the bigger the push. A KBC-like structure could provide a shift of several percent, shaving off part of the discrepancy between early and late universe measurements. Yet it seems unlikely, given what we currently know, that the void alone can fully reconcile the two. There is still a residual tension that demands either remaining systematics or genuinely new physics. You might feel a little disappointed by that. It would have been elegantly simple if the answer were that we just live in an odd patch of the cosmic web and that all the fuss was a kind of geographical misunderstanding. Instead, we are left with a more complicated and more interesting situation. Our location probably does matter. Our void probably does tilt some measurements, but it shares responsibility for the tension with other suspects, from subtle observational biases to the possibility that our cosmological model needs an upgrade. In the next part, we will move from hand-built models to full-scale simulations and see what it is like to inhabit a universe where many observers live in many different environments. There, inside the computer, we can ask a question that the real universe answers only once. What fraction of observers live in voids like ours? What do they see? And how often do they end up scratching their heads over the expansion rate in exactly the way we do? To really understand what it means to live in a cosmic void, cosmologists do something wonderfully audacious. They build universes from scratch inside a computer, then drop imaginary observers into them and ask what those observers would see. In that virtual multiverse, you're not limited to one cosmic address and one history. You can sample a huge variety of environments, from crowded clusters to lonely voids, and watch how each one shapes the measurements an astronomer would make. It is the closest thing we have to re-rolling the dice of creation to see how unusual our situation really is. The starting point for these simulations is the early universe. We know from the cosmic microwave background that the young cosmos was nearly uniform, with tiny ripples in density imprinted across space. Those ripples can be described statistically. They have a certain typical size and amplitude. In a simulation, you generate a three-dimensional field of these tiny fluctuations. Draw them from the same statistical recipe that fits the microwave background, and then let gravity and expansion evolve the field forward in time. Dark matter collapses into halos. Gas falls in, cools, and eventually forms galaxies. A cosmic web appears, not because anyone drew it, but because the underlying physics demands it. Modern simulations track billions of particles representing dark matter and gas in boxes that can be hundreds of millions of light-years on a side. They follow the expansion of space, the growth of structure, and sometimes even the formation of stars and black holes. You can tweak the ingredients, changing how much dark matter and dark energy you include or how they behave, and watch how the resulting cosmic web differs. If your simulated universe matches the real one in its large-scale patterns, you gain confidence that your model captures the essential physics. Once you have a virtual universe, you can turn it into an observatory. Choose a particle or a galaxy to stand in for the Milky Way, and imagine that as the location of an observer. From that point, you can measure the local density field, count nearby galaxies, and compute how fast things appear to recede. You can construct a Hubble diagram, the relation between distance and recession speed, in exactly the same way an astronomer does with real supernovae. Then you move your observer to another galaxy and repeat the exercise. Over and over, across thousands of locations, you build a distribution of possible local measurements. This distribution is what people mean when they talk about cosmic variance. Even in a perfectly known cosmology, different observers will measure slightly different values for quantities like the Hubble constant, because they live in different environments. Some sit in slightly overdense regions where gravity has tugged harder on their surroundings. Others, like potential inhabitants of a void, sit in slightly underdense regions where expansion is less hindered. The simulated universe tells you how wide this scatter should be. If the spread in local Hubble values is small, then any large disagreement with the global value is hard to explain as mere chance. To study life inside bubbles specifically, cosmologists apply an extra filter. They identify regions in the simulation that qualify as sizable voids, underdense over large radii in a way that resembles the inferred KBC structure. Then they place observers only inside those voids and ask what they would measure. These are void observers, a special subset of all possible cosmic citizens. For each one, you can trace light rays from distant simulated supernovae through the lumpy density field, compute redshifts and luminosity distances, and fit a Hubble constant from the resulting data. The results follow the intuition we built earlier. Observers in deep voids tend to infer higher Hubble values than the global average. In some simulations, that shift can be several units on the usual scale, enough to move the local measurement noticeably upward. When you compare the distribution of Hubble constants for all observers to the distribution for void observers only, the void group is skewed toward larger values. They really do live in faster expanding patches. The simulations show that this is a robust effect, not a mathematical trick. Local underdensity genuinely speeds up the apparent expansion seen by those within it. The question, as always, is whether the effect is big enough. In many studies, even observers in quite extreme voids do not see values as high as the most tension-filled local measurements. The void environment boosts their Hubble constant by a few percent compared to typical observers, but the gap between early universe and late universe values often remains larger than that. The shift helps, but does not fully close the distance. This echoes what we saw from simpler analytic models. The KBC Void, if it matches the depths and sizes tested in simulations, can meaningfully nudge our measurements, yet struggles to be the sole culprit. Simulations also let you ask how likely it is to find yourself in such a void in the first place. You can count how many galaxies in the simulated universe inhabit regions that match the KBC profile. In many standard cosmologies, that fraction is small. Not zero, but comfortably below what you would expect if every other galaxy lived in an equally dramatic underdensity. This is where the uncomfortable feeling returns. If void observers like us are rare in the simulations, and they are also the ones who experience a Hubble tension similar to ours, then our own puzzle begins to look less like a generic feature of the model, and more like a peculiar headache of a small minority of cosmic vantage points. There is another subtle lesson that emerges from these experiments. The impact of a void on local measurements depends not only on its depth and size, but also on how the rest of the universe is arranged around it. A void embedded in a symmetric environment has different effects than one surrounded by a lopsided arrangement of clusters and filaments. The line of sight to each supernova passes through a different set of structures. Some directions may be more distorted than others. When you average over many supernovae in different patches of sky, some of these effects cancel, others do not. The detailed pattern of structure matters as much as the fact of underdensity itself. Simulations are the only practical way to capture that complexity. Perhaps the most important role of these virtual universes is not to provide a final answer, but to keep us honest. They show that local environment can and does shift the numbers we infer from the sky. They quantify those shifts and reveal how strongly they depend on our cosmological assumptions. They warn us when a proposed explanation demands voids that are far rarer or more extreme than anything the model naturally produces, and they remind us that any single observer, no matter how clever, samples only one thin path through one particular realization of the cosmic web. From inside the simulation, you can switch perspectives with a keystroke. From inside the real universe, you're stuck in your one bubble, looking outward and trying to guess how typical you are. The KBC Void, if it is real, suggests that we may not be as average as we once hoped. The simulation suggests that even so, our environment alone is unlikely to account for every piece of the Hubble tension. In the next part, we will step away from the machines and turn to a more human question. If our neighborhood is unusual, does that say anything about why we're here, or are we just telling ourselves stories in the dark? By now, our story has become strangely personal. We started with galaxy maps and simulations with equations and density fields. Yet beneath all that is a softer question that does not fit neatly into a data table. If our galaxy really does live in a vast underdense region, does that say anything about why we're here? Are we special in some deep way, or are we simply the kind of survivors who can only ever wake up in certain kinds of neighborhoods? Every science student learns that we should not put ourselves at the center of the universe. Earth is not special. The Sun is not special. The Milky Way is not special. At least that is the mantra. But there is another kind of specialness that is harder to avoid. You and I can only exist in places where conditions allow for long-lived stars, stable planets, and chemistry rich enough to build complex molecules. That simple fact creates what physicists call a selection effect. We only get to observe the kinds of regions where observers can arise. You see selection effects all the time in everyday life. If you walk through a busy beach town, it may feel like everyone in the world lives near the ocean. If you count how many people you know with internet access, you might underestimate how many live without it. Your personal sample is biased toward the environments that you yourself inhabit. The same logic applies on cosmic scales. Wherever intelligent beings arise, they will naturally tend to find themselves in galaxies and regions that are good at producing and maintaining life-friendly conditions. As soon as you admit that, a tempting idea appears. Maybe we live in a void because voids are better for life. Perhaps crowded regions of the cosmic web are more violent. Galaxies there collide more often. Supernova explosions and bursts of high-energy radiation may be more frequent. Gravitational tugs from passing stars could disrupt planetary systems. By contrast, a galaxy in a relatively empty region might enjoy a quieter history. Fewer close encounters, fewer catastrophic events, more time for biology to slowly experiment. In that picture, voids are not cosmic deserts. They are peaceful suburbs. To see whether this story holds up, we need to think about what makes a region hospitable. One ingredient is heavy elements. The first generations of stars formed almost entirely from hydrogen and helium. They had no planets like Earth. Heavier elements such as carbon, oxygen, silicon and iron had to be forged in stars and scattered by stellar deaths. Regions with a rich history of star formation and supernovae should have more of these elements mixed into their gas. That in turn allows for rocky planets, diverse chemistry, and perhaps life. On that front, dense regions of the universe have an advantage. They simply form more stars and recycle more material. Another ingredient is stability. You want planets in long-lived orbits, around stars that do not flare too violently, in parts of galaxies where catastrophic events are not common. Being too close to the galactic center might expose you to more supernovae and energetic outbursts. Being too far out might leave you starved of heavy elements. Somewhere in between, there is a sweet spot where conditions are neither too harsh nor too poor. This idea has led to the notion of a galactic habitable zone, a band where the balance of metals and safety might be most favorable. Voids complicate this picture. Galaxies in underdense regions tend to be more isolated. They experience fewer major collisions. Their star formation histories can be more gentle. That sounds good for stability. At the same time, they often have lower overall densities of gas and sometimes lower metallicities, meaning fewer heavy elements per unit mass. That sounds less good for building rocky planets and complex chemistry. It is not obvious which effect wins. Does the quiet isolation of a void outweigh its relative poverty in enriched material, or is the opposite true? Right now, we do not know. We have only one confirmed example of a life-bearing planet and one small patch of cosmic environment associated with it. We can study how common Earth-sized planets are around different kinds of stars. We can measure metallicities of galaxies in different regions and compare their star formation histories, but we cannot yet link those statistics directly to the probability of intelligent life. The biology is too uncertain. We do not even know whether life arises easily when given the right ingredients, or whether it is an incredibly rare fluke. Because of that ignorance, anthropic reasoning slips easily into philosophy. The anthropic principle in its simplest form just says that any observation you make must be compatible with your existence. That is obvious once you say it out loud, yet people are tempted to push it further. They might say that we live in a void because only voids can nurture beings like us, or that certain values of cosmic parameters are observed because only those values allow life to appear. At its best, this style of argument can rule out obviously impossible scenarios. At its worst, it becomes a kind of cosmic just-so story. If we are not careful, we end up in a circle. We notice that our environment has some unusual feature. We speculate that this feature is important for life. Then we explain our observation of the feature by the fact that we are alive. That feels satisfying for a moment, but it has not really predicted anything new. It has not given us a testable outcome. In the case of the KBC Void, we can always say that maybe voids are better for life, but without an independent way to measure life across different cosmic environments, that remains a narrative rather than a conclusion. Some researchers try to sharpen anthropic reasoning into a more quantitative tool. They imagine many possible universes with different parameter values and ask in how many of those universes complex structures and observers would be likely to arise. They then compare that distribution to the actual values we measure. It is a bold program, but it depends heavily on assumptions about what counts as an observer and what conditions life requires. Those assumptions are guesswork. Until we know much more about biology on other worlds, any claim that our local void is explained by anthropic selection will rest on a lot of uncertain steps. So are we special or just survivors? From a strict physical point of view, there is no evidence that our presence inside a suspected void required that void to exist. The KBC structure may make our measurements of cosmic expansion a little more awkward, but we do not yet see clear signs that it uniquely nurtured our origin. We might be living in a slightly unusual neighborhood for reasons that have nothing to do with life, or our location might one day turn out to fit into a broader pattern of cosmic habitability that we have not yet uncovered. What we can say with confidence is more modest. Any observers in the universe will always see the cosmos from a biased vantage point. They will be more likely to live in regions compatible with their own existence, and less likely to arise in environments that suppress complex structures. That is a kind of cosmic humility. It tells us that our perspective is not random. It is filtered. But it does not yet tell us that our local void is part of a grand design. In the next part, we will leave these philosophical shadows and return to the bright light of data. If the KBC void is real and plays any role in the Hubble tension, there should be ways to test that with future surveys. We will look at the concrete observational strategies that can confirm or refute the void hypothesis and help us decide whether our quiet neighborhood is just a curious footnote or a key player in the story of cosmic expansion. Up to this point, the KBC void has been a kind of ghost. It shows up in galaxy counts, in simulations, in our imagination, but always at one remove. To decide whether it is real and important, we need tests that go beyond suggestive patterns. We need ways to map the matter around us directly, measure how space is expanding through it, and see whether our neighborhood truly behaves like a giant bubble in the cosmic web. The comforting part is that this is not a vague dream. There is a concrete set of observations that can confirm or rule out the void hypothesis in the next generation of surveys. The first step is simply to count better. Early studies of the KBC void stitched together galaxy surveys that were never designed for this specific purpose. They had patchy sky coverage and different sensitivity limits. A decisive test needs deep, uniform, all-sky maps of galaxies that reach well beyond the suspected edge of the void. Infrared surveys, which see through much of the dust in the plane of the Milky Way, can help fill in the blind spots. If we truly live in a large underdense region, then no matter how you slice the data, the average galaxy density in shells around us should sit low for hundreds of millions of light-years before rising toward the global mean. Better galaxy maps are only the start. Matter that does not shine still shapes the universe. Dark matter dominates the mass budget, and any serious test of the void hypothesis must measure that as well. One of the most powerful tools for this is weak gravitational lensing. As light from distant galaxies passes by foreground structure, its path is slightly bent by gravity, distorting the shapes of those background galaxies by a tiny amount. By measuring those distortions statistically across the sky, you can reconstruct a map of the total matter distribution, luminous and dark together. In such a map, a true void would appear as a broad region of reduced lensing signal, a great shallow bowl in the gravitational field. Another critical probe is the peculiar velocity field, the pattern of motions of galaxies on top of the smooth Hubble expansion. If we live inside an underdense bubble, galaxies inside it tend to flow outward toward the denser walls, while galaxies beyond its edge feel a net pull inward. Measuring these flows is hard because you need independent distances as well as redshifts. Yet with enough distance indicators, you can build a three-dimensional velocity map. A consistent pattern of outward motions around us on very large scales would be a smoking gun for a substantial local underdensity. There are more subtle tools as well. The way hot gas in galaxy clusters distorts the cosmic microwave background carries information about large-scale motions of matter. This is known through a scattering effect that imprints tiny shifts in the background light. A coherent flow pattern on scales comparable to the suspected void would leave a signature in those distortions. Detecting such a signal cleanly is extremely challenging, but future data from high-resolution microwave experiments could help check whether our region behaves like a giant evacuated bubble or like just another mildly lumpy patch. Beyond mapping density and motion, we can attack the problem from the distance side. The distance ladder that gives us a high local Hubble constant relies mainly on stars and supernovae, but there is an independent way to measure cosmic distances that has nothing to do with how bright things appear. Gravitational wave events from merging neutron stars produce ripples in space-time, whose strength falls in a known way with distance. Detect those waves and you get a direct distance estimate. If you can also identify a light-emitting counterpart and measure its redshift, you have what people call a standard siren, an entirely separate rung of the distance ladder. Standard sirens are especially interesting in the context of a void because they can be scattered across a wide range of distances. With enough events, you can compare the expansion rate measured inside the suspected underdense region to the rate measured well beyond it, using the same method for both. If the KBC void is real and significantly speeding up local expansion, that difference should show up in the standard siren Hubble diagram. If the measured Hubble constant remains high, even for events that lie far outside our supposed bubble, the void explanation loses some of its appeal. Other distance probes can join the test as well. Strongly lensed quasars, where light from a distant source is bent into multiple images by a foreground galaxy, have time delays between their images that depend on the expansion rate. Large samples of these lenses spread across the sky and out to high redshift can provide another check on the global Hubble constant that sidesteps some of the systematics of supernova surveys. Baryon acoustic oscillation measurements, which track a preferred scale imprinted in the distribution of galaxies, offer yet another way to link distances and redshifts on scales far larger than any one void. The power of this multi-pronged approach is that it does not let the void hypothesis hide in a single type of data. A real KBC-sized underdensity must leave a consistent trail across many independent observables. It must appear in galaxy counts, in lensing maps, in peculiar velocity flows, and in the detailed pattern of distances inferred from both light and gravitational waves. If some of those lines of evidence say yes while others say no, we will know that at least one of our assumptions is off. Perhaps the void is shallower than early studies claimed. Perhaps other systematics are at work. Future observatories are being built with exactly this kind of precision in mind. Wide-field optical surveys will chart billions of galaxies and their shapes. New spectroscopic campaigns will measure redshifts for huge samples, turning two-dimensional sky maps into three-dimensional webs. Gravitational wave detectors will grow more sensitive, catching more standard siren events each year. None of these projects is aimed solely at the KBC void, yet together they create an environment where the hypothesis can be tested as sharply as any other. In the end, testing the void hypothesis is less about defending one idea and more about stress testing our entire picture of the cosmos. If the data confirm that we live in a large underdense region and show exactly how it affects our measurements, we will fold that into our understanding and move on with a slightly more complicated but more accurate story. If the data instead reveal that the void is small or illusory, we will know to look elsewhere for the roots of the Hubble tension. Either way, we will have turned a vague suspicion into a clear question that the universe itself can answer. By now you might imagine cosmology as a battle between nature and theory. On one side, the universe with its galaxies and voids. On the other, equations and simulations. In practice, there is a third player that quietly sits in the middle and shapes everything we conclude. The data pipeline. Every result we talk about passes through a chain of instruments, calibrations, algorithms, and human choices. The KBC void and the Hubble tension are not just features of the cosmos, they're also reflections of how we collect and process information about it. Think about what happens when a telescope observes a distant galaxy. The raw signal is a pattern of counts on a detector. Those counts are affected by the atmosphere, the optics, the detector response, stray light, cosmic rays, and more. Then software subtracts backgrounds, corrects distortions, and turns those counts into a flux and a position on the sky. That flux is later translated into a brightness. That brightness is corrected for dust and instrument effects. Only at the very end do we treat the result as a data point on a plot of distance versus redshift. At every step, there are assumptions about what is noise and what is signal. Now zoom out to an entire survey. You have millions of galaxies across a large patch of the sky. Some are easy to detect. Others are faint and barely rise above the noise. You must decide how faint you're willing to trust. Cut too bright and you miss a lot of the universe. Cut too faint and you risk filling your catalogue with spurious detections and mismeasured objects. These choices affect how many galaxies you count in each volume of space. When you're trying to see whether our region is underdense, such choices can tilt the answer. A slightly stricter brightness cut might make a real void look deeper. A more generous one might fill it back in. Dust within our own galaxy adds another layer of trouble. The Milky Way is not a clean window. It is a smeared band of stars, gas, and fine particles that absorb and scatter light. Regions near the galactic plane are especially affected. If your dust maps underestimate how much light is lost in those directions, you will undercount background galaxies there. If they overestimate the extinction, you will overcorrect and create artificial overdensities. Infrared surveys help by seeing through much of the dust, yet even they need careful calibration. The apparent shape and depth of any local void can be twisted by how well we handle this foreground veil. Distance indicators bring their own complications. The brightness of Cepheids depends on their chemical composition and environment. Type 1. A supernovae are not perfectly identical. Their light curves must be standardized using empirical relations. Those relations are derived from a training set of nearby events. If that training set is biased towards certain types of host galaxies or star formation histories, the standardization may bake in unnoticed preferences. When those standardized candles are used to build the distance ladder, small shifts in their inferred luminosities can propagate into shifts in the Hubble constant. It gets even more tangled when you combine datasets. The local Hubble value might rely on one set of instruments and reduction pipelines, while the cosmic microwave background result uses a completely different family of detectors and software. Each team spends years validating their methods, running internal cross-checks, and searching for systematics. Yet the pipelines have different cultures, different historical legacies, and different default assumptions. When their answers disagree, it is tempting for each side to suspect the other. The reality is that both could be almost right and still slightly biased by unrecognized details in their processing. History offers some humbling examples. There have been apparent anomalies in large-scale flows of galaxies that weakened when better distance measurements arrived. There have been hints of strange features in the cosmic microwave background that faded as data analysis improved. Even the value of the Hubble constant itself has drifted over the decades as astronomers revised calibrations, discovered new classes of stars, and corrected for overlooked effects like metallicity. Many of those early tensions taught the field to be cautious. Some spectacular claims quietly evaporated once the community learned to handle the data more carefully. This does not mean that every discrepancy is an illusion. It means that precision cosmology lives in a narrow space where small systematic errors can mimic the effects of large physical differences. A bias of a few % in brightness calibration, a mild selection against certain host galaxies, or a slightly inaccurate dust map can produce shifts that are comparable in size to the Hubble tension itself. When we then add the possibility of a real physical effect from our local void, the landscape becomes a thicket of overlapping influences. Untangling them is more like debugging a complex program than reading a pure signal from nature. The KBC Void is a perfect case study in this complexity. The original claim grew out of galaxy counts and luminosity densities stitched together from multiple surveys. Each survey had its own footprint, depth, and selection function. Correcting for those differences requires models of how galaxies populate halos, how star formation varies with environment, and how complete the catalogues are at each distance. If any of those ingredients is slightly off, you can either exaggerate a real underdensity or suppress one that is there. That is why some follow-up studies have found a milder void, while others still see a strong dip. They are not simply disagreeing with the same numbers, they are building those numbers in different ways. In a sense, the data pipeline is itself part of the experiment. Changing how you process the information is like tuning a new piece of apparatus. Good practice demands that teams make their methods as transparent and reproducible as possible. That means publishing code, documenting selection criteria, and releasing raw data so others can reanalyze it. Over time, different groups applying different pipelines to the same sky will either converge on a consistent picture or expose where assumptions are steering the results. The story of the void and of the Hubble tension will likely be shaped as much by this slow collective debugging as by any single new observation. There is a deeper lesson hiding here that reaches beyond cosmology. When we say that the universe is accelerating or that we live in an underdense region, we are really making statements about numbers filtered through instruments, models, and human judgment. The raw universe has no Hubble constant written on it. It has galaxies and light and gravity. The constants and voids exist at the end of a very long chain of reasoning. Recognizing that does not make them less real. It simply reminds us that our picture of reality is always mediated and always provisional. In the next part, we will step back from the technical tangle and ask what this entire episode tells us about science itself. How does a field move forward when its measurements are exquisitely precise, yet disagree in stubborn ways? What does it mean to live, both intellectually and emotionally, with tensions that may take years or decades to resolve? The KBC Void and the Hubble constant may turn out to be passing characters in that story, but the way we handle them reveals something lasting about how we explore a universe that is stranger and more complicated than our pipelines can ever fully capture. Stand outside on a clear night and look up, and the last word that comes to mind is empty. The sky feels crowded with stars. The Milky Way is a dense band across the darkness. You might even feel slightly overwhelmed, as if the universe is pressing down with sheer quantity. It takes an act of imagination to remember that almost everything you see is confined to one galaxy, one thin disk of stars inside a much larger structure, and that even this structure may be drifting through a region that is unusually sparse. The idea that we live in a giant cosmic underdensity sounds abstract, yet it quietly touches how we think about our place in the universe. For centuries, that question has mostly moved in one direction. Each major discovery has pushed us down from a pedestal. Earth is not at the center of the solar system. The Sun is not at the center of the galaxy. The Milky Way is not the whole universe. Our observable patch is not all that exists. The Copernican instinct has become a habit. When in doubt, assume we are not special. The cosmological principle formalized that instinct on the larger scales, telling us that the universe should look roughly the same from any galaxy if you zoom out far enough. Living in a big void feels uncomfortable in that context. On one reading, it sounds like a reversal of the trend. We are no longer ordinary citizens of a typical district. We are residents of a rare kind of neighborhood, the owners of cosmic real estate that most galaxies never see. That can trigger two opposite stories in the mind. One is flattering. Perhaps our quiet surroundings are somehow chosen, a gentle enclave tailored for life and thought. The other is almost mocking. Perhaps we are not central after all, not important enough to be near any of the great clusters and walls, tucked instead into the empty margins of the cosmic web. Both reactions give the void more emotional weight than it deserves. They treat the distribution of galaxies like a hidden message about our worth. Reality is more indifferent. The large-scale structure of the universe is not arranged to send us signals about our status. It is what happens when quantum fluctuations, gravity, and expansion are left to play out over billions of years. Clusters and voids are not medals or punishments. They are side effects of simple rules run for a long time. Interpreting them as praise or insult says more about our psychology than about the cosmos. Yet it is natural to look for narrative patterns. The KBC Void arrives in a story already packed with themes of demotion and decentralization. So we reach for familiar metaphors. We ask whether this is another step in the same direction, or a twist. We wonder whether the apparent rarity of our environment should make us suspicious of our models, or simply more aware of selection effects. We treat the universe like a book that might be hinting at a plot. The risk is that we start reading personal meaning into features that are only loosely connected to our existence. There is another way to frame it that is quieter. Instead of asking whether living in an underdense region makes us special, we can ask what it does to our experience of understanding. Knowing that our cosmic address is not perfectly average is a reminder that every view of the universe is taken from somewhere, with all the biases that implies. We do not get to float in a mythical no-man's land outside space and time, surveying the cosmos from a perfectly neutral vantage point. We are always located, always embedded, always peering outward through the lens of a specific history and environment. From that perspective, the void is not an insult or a promotion. It is a piece of context. It tells us that some of the numbers we infer from the sky are coloured by the particular patch of web we inhabit. It nudges us toward a more mature humility, one that goes beyond saying we are not at the centre. Instead, we admit that even our efforts to be objective are shaped by the local arrangement of matter and the tools we have built on one small planet. The KBC Void becomes a symbol of that fact, a reminder that our deepest theories still rest on the shoulders of specific measurements made from a specific place. There is also a kind of strange beauty in the idea that we live in an unusually quiet region. It fits, in a way, the mood of modern cosmology. We already know that most of the universe is made of dark things we cannot see directly. We already know that the visible galaxies are like a thin glaze on top of a much larger invisible structure. Learning that our own galaxy may be drifting through a broad, underpopulated basin deepens that sense of cosmic loneliness, but not necessarily in a frightening way. It can also feel like stepping into a wide, empty landscape where the silence itself is part of the charm. If you enjoy looking at the night sky precisely because it gives you a sense of peace, the idea that we live in a region with fewer galaxies than average carries an odd emotional resonance. It suggests that the calm you feel is not entirely imaginary. Our corner of the cosmic web might genuinely be a little less busy, a little less violently tangled than many other places. We do not know whether that matters for life, but it certainly matters for story. It changes the metaphor. We're not living in the downtown of the universe. We're out in a kind of vast suburb, with long distances between neighbours and a lot of dark road between streetlights. At the same time, the void brings back a lesson that science has been teaching in different forms for a long time. The universe is under no obligation to match our intuitions about fairness or typicality. We might have hoped that our environment would be a perfect representative of the cosmic average, so that our measurements could speak for everyone. Instead, we may have to accept that our data are not taken from a perfectly generic patch. That does not make them useless. It simply means that part of the job of cosmology is to correct for our own cosmic parochialism. In the end, the philosophical weight of the KBC Void may not lie in whether it exists or how big it is, but in how we respond to the possibility. Do we rush to weave it into comforting fables about why we are here? Do we ignore it because it complicates a clean picture of a perfectly homogeneous cosmos? Or do we let it remind us that even our grandest theories are stitched together from local experiences in a universe that is not obligated to be simple, symmetric, or emotionally tidy? The striking thing is that we can have this conversation at all. From one small planet in a dim spiral arm, we have inferred not just that the universe is expanding, not just that it has dark matter and dark energy, but that our galaxy may sit in a vast region of slightly reduced density, stretching hundreds of millions of light years. That is a remarkable act of collective perception. The emptiness around us becomes part of our identity, not in the sense of cosmic importance, but in the sense that it shapes the questions we ask and the puzzles we face. In the next part, we will turn from philosophy back to practice and look at what this whole saga tells us about the way science actually moves forward. The KBC Void and the Hubble tension are still unresolved. Yet even in their uncertainty, they show how a field can live for years with a nagging discrepancy, and use that discomfort as fuel rather than as a reason to despair. If you step back and look at this whole saga, it feels messy. We have careful measurements that disagree. We have galaxy maps that hint at a giant local void but do not quite nail it down. We have simulations that help and confuse at the same time. Nothing is wrapped up with a bow. This is not a bug in the scientific process. This is what the middle of the story looks like. Science spends most of its life here, in the gap between what we can measure confidently and what we can explain cleanly. When you read a textbook, you see the finished parts. Gravity pulls planets into orbits. Light behaves like both a wave and a particle. The universe is expanding. Each statement sounds simple and inevitable. What you do not see is how long the field spent living with contradictions before those ideas settled. Mercury's orbit refused to match Newton's laws. The spectrum of hot objects made no sense in classical physics. The speed of light refused to add up the way everyone expected. For years, people added patches, proposed fixes, and argued over systematics. Only later did relativity and quantum theory arrive to make those tensions feel obvious in hindsight. The KBC Void and the Hubble tension sit in that same uncomfortable zone. They are sharp enough to be annoying, yet not overwhelming enough to force an immediate revolution. If the local and global Hubble values differed by a factor of 2, we would know instantly that something huge was wrong. Instruments would be torn apart, models would be thrown out. Instead, the disagreement is a small fraction of that, large enough to be statistically significant, small enough to be plausibly blamed on subtle biases. That is the perfect size to provoke years of careful work. In this phase, science looks less like a march and more like a nervous shuffle. Teams dig deeper into their own methods, hunting for systematics they might have missed. New surveys are designed with better calibration in mind. Independent groups try to measure the same quantities with completely different techniques, hoping to either confirm the problem or make it go away. The literature fills with papers that start from the same data and reach slightly different conclusions. From the outside, it can look like confusion. From the inside, it is a necessary kind of friction. There is a real emotional side to this. Scientists are human. They invest years of effort into a particular instrument, survey, or analysis pipeline. When their results conflict with others, it touches pride and identity. It is tempting to decide early that the other side must be wrong, or that a favourite explanation, like a local void or a new particle, must be right. Good practice asks for something harder. You have to hold multiple possibilities in your head at once. Perhaps the void is real and important. Perhaps it is real but modest. Perhaps it is mostly an artifact of selection effects. Perhaps the tension points to new physics. Perhaps it does not. You keep all of those doors open while you collect more evidence. History suggests that many tensions do not survive this process. Some disappear when measurements improve. Others dissolve when people notice that they have been comparing slightly mismatched quantities. A famous example is the solar neutrino problem. For decades, detectors saw only about 1/3 of the expected neutrinos from the Sun. The tension looked serious. Slowly, as experiments improved, the puzzle sharpened. Eventually, it pointed to a real physical effect, neutrino oscillations that expanded our understanding of particle physics. The key is that no one knew in advance whether the tension would evaporate or lead to something new. They only knew it was worth taking seriously. The Hubble tension and the KBC Void could fall on either side of that divide. It is possible that future surveys will show that our local underdensity is mild, that systematics in our distance ladders were larger than we thought, and that the early and late universe values quietly drift together. It is also possible that the disagreement will persist or even grow as error bars shrink. In that case, the tension might become the kind of stubborn anomaly that forces a real change in the cosmological model. Maybe dark energy is more complicated than a simple constant. Maybe the early universe had an extra ingredient we have not accounted for. Maybe gravity itself needs adjusting on large scales. The important thing is that science has room for all of these possibilities without needing to pick a favourite too soon. The method is deliberately conservative. You do not claim new physics when a more mundane explanation will do. You also do not ignore persistent discrepancies just because the existing theory is elegant and successful. Instead, you treat tension as a signal. It tells you where to point new telescopes, where to invest more computing power, where to scrutinize your assumptions. There is a quiet discipline involved in living with unfinished stories. You have to get comfortable saying 3 words that are strangely hard in public. We do not know. That does not mean we know nothing. In this case, we know a great deal. We know that the universe is expanding. We know that dark matter and dark energy dominate its contents. We know that structure grows from early ripples into the filaments and voids we see today. Within that broad picture, we now have a set of precise measurements that do not fully align. The gap is small enough that everyday life is unaffected, yet large enough to matter for the deepest questions about what the universe is made of. From a distance, this might feel frustrating. Where is the grand answer? Where is the final theory? Up close, the situation is more inspiring. We are lucky to live at a time when the biggest uncertainties are not about whether the universe is expanding at all, but about how precisely it does so, and whether our place inside the cosmic web tilts our view by a few percent. These are the kinds of questions you only get to ask once you have already solved a long list of harder problems. The remaining tensions are a sign that our instruments and models are now sharp enough to notice small misalignments. Living with that kind of tension is not a failure of science. It is a sign that science is doing exactly what it should, pushing numbers until they hurt, comparing independent paths to the same quantity, refusing to smooth over inconvenient discrepancies. The KBC Void might one day be downgraded to a footnote, or it might be promoted to a key clue. The Hubble tension might fade, or it might lead to the next major shift in our understanding of the cosmos. Either way, the process of wrestling with them strengthens the field. It forces us to audit our assumptions, refine our tools, and learn how to tell the difference between noise, bias, and real new physics. In the final part, we will return to where we began, to the image of our galaxy adrift in a giant hollow in the cosmic web. We will ask what it means, personally, to know that we may live in one of the emptier neighborhoods of a universe already dominated by darkness, and how that knowledge can deepen rather than diminish the quiet awe you feel when you look up at the night sky. Imagine the cosmic web from far above, as if you could step outside the universe and look back in. You would see bright knots where clusters live, long filaments of galaxies stretching like tendons, and in between, great dim basins where almost nothing shines. Somewhere in one of those basins is a small spiral galaxy with a yellow star and a rocky world where creatures have learned to map the very void they inhabit. That is us. We are not watching this story from the outside. We are inside the hollow, using faint light from distant galaxies to sketch the shape of our own cosmic solitude. Over the last century, we have pieced together a picture that would have stunned every earlier generation. The universe is expanding. Space itself carries galaxies apart. Most of the matter out there is dark. Most of the energy is hidden in a form that pushes on the fabric of space-time. From that strange mixture, structure grows. Overdensities collapse into clusters and filaments. Underdensities swell into voids. In that context, the KBC Void is not an error or a flaw. It is one of the natural outcomes of a universe left to run its own rules for billions of years. Our journey through this story has been less about decorating that picture, and more about understanding what it means to inhabit it. We learned how tiny ripples in the early cosmos seeded the galaxy patterns we see today. We watched astronomers turn a flat sky into a three-dimensional map with redshifts and standard candles. We saw how careful counts of starlight and galaxies hinted that our region is underdense on vast scales. We met the Hubble tension, a disagreement between early and late ways of measuring expansion that refuses to quietly vanish. And we saw how a local void might tilt our view of that expansion without fully explaining the puzzle. Along the way, the universe kept resisting simple stories. The KBC Void turned out to be neither a trivial bump nor a clean solution. Simulations showed that some observers do live in large underdensities, but not many. Data pipelines showed how sensitive our conclusions are to the way we count and calibrate. Philosophical instincts tried to pull the void into narratives about being special or forgotten, and the evidence refused to cooperate. Reality stayed in that awkward middle ground where the facts are sharp enough to matter but not sharp enough to close the case. So what do we do with that? As people, rather than as equations? One option is to shrug and say that a giant underdensity is just another fact to file away, like the tilt of Earth's axis or the mass of the proton. The cosmos is what it is. Our feelings about emptiness do not change that. There is a certain hard clarity in that view. It keeps our attention on the work. Count better, map better, reduce biases, design new surveys. Let the void either harden into a confirmed structure or dissolve into the background as methods improve. But there is another, gentler way to let this information in. When you hear that we may live in a region with fewer galaxies than the cosmic average, you can treat that as a kind of cosmic mood. Our galaxy drifts through a slightly quieter volume. Signals from other great structures have farther to travel. The nearest massive clusters sit at the edges of our basin, not right on top of us. For a civilization trying to take its first careful measurements of the universe, that might not be the worst place to start. The emptiness is not hostile, it is just spacious. It gives us room to think. It also sharpens a deeper kind of humility. We often say that we are small compared to the cosmos. The void adds a twist. We are small even compared to the quiet region in which we live, and that region is itself small compared to the full web. Our entire history of philosophy, art, science, and conflict has unfolded inside a slight dip in a background density field. On the larger scales, that dip matters for how we infer global numbers like the Hubble constant. Yet on human scales, it is almost comically irrelevant. The pull of a nearby mountain has more immediate impact on your life than the underdensity of 100 million light-years of space. Paradoxically, that mismatch between personal and cosmic scales can be comforting. It means that the universe is not finely tuned to narrate our story. It is not sending us messages through the exact size of a void or the exact value of an expansion rate. Those numbers are clues about how physics works, not about what we should do with our brief time here. The meaning we draw from them is something we create, not something we discover already written into the distribution of galaxies. One possible meaning is this: if we can infer a giant underdensity around us, we are already very good at listening. From a thin atmosphere on one planet, we have measured the afterglow of the young universe, mapped the motion of distant galaxies, weighed invisible matter, and noticed that our own neighbourhood may be slightly unusual. The fact that we can argue about whether a percent-level shift in a cosmological parameter is due to a void, a bias, or new physics is a sign of how far our curiosity has taken us. Emptiness, in that sense, is not a mark of being overlooked. It is a background against which our ability to understand stands out more clearly. There is also a quiet lesson about uncertainty. The void and the Hubble tension remind us that even in a mature science, some questions remain open for a long time. The numbers do not line up perfectly. Different methods point in slightly different directions. Explanations jostle for attention. That is not a failure. It is a sign that we are still in motion. Living in a universe that contains a KBC-sized question mark is another way of saying that there is still real work to do and real discoveries ahead. The emptiness in our region becomes a symbol of the unfinished parts of our understanding, the spaces where new ideas might grow. So the next time you step outside at night and feel that particular mix of calm and unease that the sky can bring, you might let this thought hover at the edge of your awareness. Somewhere out there, beyond the faint glow of the Milky Way, the density of galaxies rises toward the cosmic average. Our quiet patch gives way to a busier web. We are perched inside the slope of that transition, using the light from those distant regions to learn not only about them, but about ourselves. We are tiny. We are parochial. We are also, improbably, able to notice that our galaxy may live in a giant patch of almost nothing and turn that fact into a question worth asking. In the end, the universe does not care that we live in a void. Yet we care because we are the kind of beings who turn geography into meaning. We take a slightly emptier neighbourhood and make it part of our shared story, another chapter in the long process of learning how to be at home in a universe that is at once deeply indifferent and endlessly knowable. The hollow around us is not a verdict. It is a vantage point, a wide and quiet balcony from which to watch the cosmos expand and to decide together what we want to understand next.